Lesson 1-2, Linearity, Intercepts, and Symmetry. First off, linear function is just a function where the variable is raised to a power no more than 1. Any linear function that can be written in the form of f(x) equaling mx plus b, and m and b are real numbers, then you would have that linear function. Linear functions are also those linear equations that are written in standard form of ax plus by equals c. So if you cannot put it into slope-intercept form or standard form, then it's not linear. A function that is not linear is called a nonlinear function. The graph of the function includes a set of points that cannot all lie on the same line, then the function is nonlinear. So that means it's going to have some curves in it, or it's going to come to a corner like that. That would be an absolute value function. Nonlinear function cannot be written in the form of f of x plus mx plus b. A parabola is a graph of a quadratic function, which is a type of nonlinear functions. Also, one last thing is it's not a function, not a linear function, if you have two variables like x and y next to each other or multiplied by each other. So let's take a look at some examples. So determine whether each function is a linear function and then justify your answer. This first one, letter A, f of x equaling 6x minus 5 divided by 3. This is also written as 2x minus 5/3, which is in f of x equaling mx plus b. So yes, it's in slope-intercept form. Next, b, 5y equals 4 plus 3x cubed. Because of this x cubed here, this is not a linear function. This would have had some bends, and the reason is because of that exponent. Next, g of x equaling 2/5 x. Yes, this is linear because this would be just saying the y-intercept is 0 and it has a slope of 2/5. Letter B is no, because I'm multiplying x and y. So that would be more of a rational function. Means you're going to end up dividing by x. This next one is in standard form. So yes, this is a linear function. Letter D, think of this as y. So it's a horizontal line because it crosses the y-axis at 5. So yes, this is linear. Letter E, f of x 3x squared plus 2. This is not because of the square. This would be a parabola shape. So no, this is not linear. And letter F, y equals 2/5 minus the square root of 3x. The x is on the outside, so the slope is actually a negative square root of 3. So yes, this is a linear function because it is in y equals mx plus b format. Our next example is dealing with graphs, and we need to determine whether each graph represents linear or nonlinear. When you see a graph, it's going to be a lot easier because you can just see, is it a straight line or is there bends, curves, or corners to it? So letter A, this would be nonlinear because it's not a straight line, because there's a bend right here. Letter B is a linear. It is a straight line. This would be in y equals mx plus b if you were to write the equation of that line. Next, letter A here would be linear. I know you don't see a line, but if you were to connect all these points in one line, then it would be a straight line. Letter B would be non-linear because you have a bend here and a bend here. So the two bends, not a straight line. Example 3, Michaela started working part-time at the local hardware store. working steadily increases for the first 5 weeks. The table shows her total earnings each of those weeks. Are her weekly earnings modeled by a linear or a non-linear function? The first thing I would do is check to see if there's a constant slope. So the weeks are increasing by ones. And down here, if I were to subtract them, 119 minus 85, you would get 34. And over here, if I were to add 119 plus 34, I would get 153. And if I add 34 here, I would get 187. Add 34 here, I would get 221. So I am increasing by the same amount and I'm adding the same amounts. So yes, this would be a linear function and it has a slope of 34. Next, Bailey and Carlos are cycling 150 miles. The table shows the distance remaining after each hour of cycling. Is the distance remaining modeled by a linear or a non-linear function? You can see my numbers are going down in the distance. If I were to find the slopes, if I use the slope formula of y2 minus y1 and divide by x2 minus x1, I did a variation of that in the previous problem. We can do the same thing here if I did these first 2 points. So this would be 128 minus 150 divided by 1 minus 0. I would have 128 minus 150 is negative 22. Divided by 1 gives us negative 22. If I did the next 2 points, I would have 106 minus 128. Divide that by 2 minus 1. I would get negative 22 over 1, over negative 1. Actually, yeah, it'd be over 1. So this is 2 minus 1. So I get negative 22. So yes, this is a constant, same slope. We would consider this one linear. Next part of our lesson is looking at intercepts of graphs. A point at which the graph of a function intersects an axis is called an intercept. It means it crosses one of the 2 axes, your x or your y axes. An x-intercept is the x-coordinate of a point where the graph crosses the x-axis, and a y-intercept is the y-coordinate of a point where the graph crosses the y-axis. A linear function has at most one x-intercept, while a nonlinear function may have more than one x-intercept. No function will have more than one y-intercept. You can only cross that once. So let's take a look at an example here. It says use the graph to estimate the x and y intercepts. So I need to find out where does it cross the x and y. It only crosses here once, and that's at 0, 0. So the x-intercept we would say is 0, 0, and the y-intercept is the y-coordinate. So we would say here x would equal 0, here the y would equal 0. When we put the intercepts in there, to find the x-intercept, it's what is x when y is 0, and the y-intercept would be what is y when x is 0. So here they're both based off of the point 0, 0. Next, this one crosses here, the x-axis there, and the y-axis here. So the x-intercept would be when y is 0, your x is 3, and the y-intercept is when x is 0, y is negative 4. Next one, this one is nonlinear. So it crosses the x-axis in these 3 places. So our x-intercepts would be -3, 0, -1, 0, and 2, 0. And the y-intercept, where is it across the y-axis? Crosses the y-axis here, which that would make that, so if they're counted by fours, that would be when x is 0, y is 12. Next, estimate the x and y intercepts of these graphs. So the x-intercept crosses right here, which means that would be 1, 2, 3, 4, 5, -5 when y is 0. The y-intercept when x is 0, y is +2. And over here, we have 1, 2, 3, 4, 5 x-intercepts. So if I were to label the 5 x-intercepts, to have a little more room, so I have -4, 0. I have -2, 0. I have 0, 0. And I also have 3, 0. And I have 5, 0. Y-intercept, where is it across the y-axis? Crosses the y-axis. This one at 0, 0. Next, use the graph to estimate the x and y intercept here. So here it crosses the y-axis there, the x-axis or the y-axis here, and the x over here. X-intercept would be when y is 0, x is 3, and the y-intercept when x is 0, y would be 1. Now, could you just put x equaling 3 and y equaling 1 for the intercepts? Yes, you may do that. Just know that there are two coordinates. If you were to be more precise, what that means for the intercepts, when x is 0, y is 1, that would be the y-intercept. When define the x-intercept, when y is 0, x would be 3. Example 6, interpret the meaning of the intercepts. So here it's going to be in a word problem. We need to determine what do those intercepts mean. It says Ricardo launches a rocket from a balcony. The table shows the height of the rocket after each second of its flight. There are two parts here. Part A, identify the x and y intercepts of the function that models the flight of the rocket. And then part B, what is the meaning of the intercepts in the context of the rocket's flight? So for part A, the x-intercept, if I go to my table, the x-intercept is when y is 0. So time is our x and height is our y. So here when y is 0, x is 8. So the x-intercept would be 8, and the y-intercept would be 15. So what does that 8 and what does that 15 mean in this context? So if we did the x-intercept first, the x-intercept would be 8, 0. So at 8 seconds, the height of the rockets is 0 feet. And then the 15 means the starting height of the rocket is 15 feet. Next, the junior class is selling raffle tickets to raise money for the prom. The table shows the number of tickets remaining to be sold at the end of each week. So at the end of 0 weeks, when they're starting, they have 500 tickets. After the first week, they have 340 tickets remaining. After 2 weeks, 210, and so forth. What are the x and y intercepts of the function modeling the ticket sales? So the x-intercept when y is 0, our x is 5. Again, our week is your X and your tickets is your Y. And then the Y-intercept, when X is 0, Y is 500. So what does the 5 mean? That means 0 tickets left after 5 weeks. And then the 500 means 500 tickets left after 0 weeks. Or you could just say they start with 500 tickets. Next is dealing with symmetry. A figure has symmetry if there exists a rigid motion that maps the figure onto itself, which just means symmetry is a reflection or a mirror image of each other. So here we have some transformations. We got reflections, we got translations. The reflection is like a mirror image. Translation is slide up, down, right, or left. Rotation is a turn, clockwise or counterclockwise, and a glide reflection. Glide reflection is just translation with reflection. We're going to focus in on the reflection and the rotation today. So when we're looking at symmetry, there are 2 types of symmetry that we're going to look at. First one is the graph has line symmetry. If it can be reflected in a vertical line, so that each half of the graph maps exactly to the other half. So the line dividing the graph into matching halves is called line symmetry. So in this example, this orange line right here that I highlighted in blue would be our vertical line of symmetry. Each point on one side is reflected in the line to the point distance, which means it's the same distance from the line of symmetry to the actual graph on the opposite side. The other one would be point symmetry. The point symmetry is when the graph is rotated 180 degrees about a point and maps onto itself. So this would be with rotation. So think of point symmetry, think of rotation. And if we went back to line of symmetry, think of mirror or reflection. So with point symmetry or rotation or point of symmetry, you pick a point on the line. So here they're choosing on the origin. And if they rotate this clockwise, it's going to match up with the other side. So just think it's like a spinner. So the image of each point on one side of the point of symmetry can be found on the line through the point and the point of symmetry distant from the point of symmetry. So now, like I could tell if I were to draw a vertical line, they're not reflected across each other. So they would be, the y coordinates would stay the same. Now for point symmetry, the opposites, you'd have opposite signs for your x and your y coordinates. Next is looking at types of functions. So you have even and odd functions. Functions that have line symmetry with respect to the y-axis are called even functions. So for every x in the domain of f, if I put a negative in there, it's still going to be the same f of x. So whether I put a positive or a negative, it's going to remain the same. There's not going to be any change. Because if this was my line of symmetry, If I put a number in there, it's still going to give me one of these two lines. The graph is not going to change. And one way when you're looking at the function itself, you're going to notice that it's going to have a degree of 2 or 4. It's going to have an even degree. So when you think of quadratic, that's a parabola. My y coordinates never change. It's just my x can be positive or negative. And because I'm going to square it, it doesn't matter. I'm still going to get the same outcome in the end. The other one is odd functions, and that goes with point symmetry. So for every x in the domain of f, if I put a negative f or negative x in for the f function, I'm now going to have the opposite sign of what I had before. That will make a little more sense once we see some examples here. So the first example, identify the type of symmetry in the graph of each function and explain. So we want to determine, does this have line symmetry, no symmetry, or does this have point symmetry? So for this one, this is a linear line, and if I were to draw a vertical line through here, if this was a reflection, this line would go out like this. But because it doesn't do that, that's not line symmetry. This would actually be rotation, because I can pick a point right here and I can rotate that this way and it will still line up 180. If I rotate it 180 degrees this direction, it'll be lined up that. Or if I went the other direction, if I went 180 degrees this way, I would still make it line up with that. Letter B over here, g of x equaling, so this one would be a line symmetry. Letter B, g of x equaling x squared minus 4x plus or minus 2. You can see I have a bend in it. I can do a vertical line, and it's an exact reflection. So this point is the same distance as this point. This is one step away. This is also one step away. So this would be line symmetry. And go back to this letter A. That one's not line symmetry. That is point. That would be point symmetry because you're rotating that around. B would be a line symmetry because I have a vertical line of symmetry that can cut that in half, and there are mirror images. Next, letter C. You can see my function there, but you'll notice in my graph, nothing looks that I could cut it in half with a line, nor is there a point. Like if I chose this point and rotate it, it's not rotated 180 degrees. It's not going to look like anything until I get to that same spot. So this would have no symmetry. And letter D, if I drew a vertical line, they're not the same on both sides of the line. So I know it's not line symmetry. If I chose a point and kept that here and rotated this way 180 degrees, it would match up with this side. Just like if this side would rotate, it would line up with that one. So this would be point symmetry. Next, identify the types of symmetry for each of these graphs. So this first one here, this one, especially because I have this bump and I have this bump, this would be a clear sign that this is no symmetry. This next one, I could draw a vertical line, but they're not the same on both sides, so it's not line symmetry. But if I rotate it across this point 180 degrees, they would line up. So this would be point symmetry. Next one is a parabola shape. So if I drew a line here, line of symmetry on both sides, they're identical. So this would be line symmetry. And letter D, I can't cut that in half vertically. They wouldn't be the same. But if I chose a point, let's just say I chose this point and then rotated it, everything around, that would match up with this side, and this would match up with that one. So this would be point symmetry. And moving to our last examples, determining if they were even or odd functions. It says determine whether each function is even, odd, or neither, and then confirm algebraically. If the function is odd or even, describe the symmetry. So for letter A, I notice that the exponent here is 3. That means it's a degree of 3. I can't draw a line of symmetry through that. So this would not be even. This would actually be an odd function. And to prove it, if I were to choose a point, so if I chose this point right here, that point was -2, 0. If I were to plug that in for letter A, all the signs should be different in my new function. Either that or easier way would be just make the x's negative. So if I had f of -x, and this would be -x cubed minus 4 times -x. So a -x cubed would give me a -x cubed, and then minus a -4 times -x would give me a +4. You'll notice that this is negative and this is positive. We had a positive x cubed and a -4. The signs are different because the signs change for all the terms. That would mean this is an odd function. So that means if this is an odd function, this would be point symmetry. This next one, letter B, you can see that my y's or my g of x's repeat, but I have one point right here that stays the same. That will be our vertex. This means this is a parabola, and a parabola has a square term in it, means a degree of 2. That would be a clue that this would be an even function, and all even functions would have line symmetry, because that would be a parabola shape. Now to check it algebraically, since I don't know the equation for this one, I would have to rely on the numbers that they gave me. So whether I put a -1 in or a +1, it still gives me the same answer of -4. So that's a clear sign that whatever I put in there, it's not going to change my y value. So everything stays the same, which would make that an even function. Now letter C, if I look at that one, I could graph that one to determine if this is an even or an odd function. But for this one, let's do it algebraically first to determine if it's an even or an odd function. So if I have a -x in here, that would mean a -x cubed plus 0.25 -x squared minus 3 times -x. Now this first one, h of -x, would equal a -x cubed. That changed from the original. The original was a positive x cubed. -0.25 x times, or -0.25 times -x squared. -x squared is x squared, so that's a positive 0.25 x squared. -3 times -x is a positive 3x. So this changed. The middle term did not change, but the other two terms did change. So if some changed and the others didn't, this would be neither positive nor negative. This is neither, and because it's neither, there is no line of symmetry. So it's either they all change even, or they all change odd, or they don't change even. And if it's a combination of both, it would be neither. On this next one here, it says assume that f is a function that contains the points 2, -5. Which of the given points must be included in the function if f is even? So if it's even, your y-coordinates cannot change. So since the y-coordinate here is -5, I have to choose the points where y is -5, which that would be -2, -5. Now for it to be odd, that means you have to have the opposite sign. So that means everything changed. So if I had a +2, I need to look at ones that are -2. So I can already cross off the ones that has a negative, that has a +2 as a x. This one doesn't have has a -2, or doesn't have a 2 or a -2 as an x. Neither does this one. So it's between these two. The one that would work would be -2 and a +5 because the signs would have changed for all of them. On the very last one, analyze the graph of f of x including 0.5x squared minus 4 to determine whether it is even, odd, or neither. Then state whether the graph is symmetric in the y-axis, which means this is line symmetry. Origin is point symmetry, or neither, because there's not any symmetry involved. So for here, if I were to check this algebraically, I could put f of -x equaling 0.5 -x and then square it minus 4. If I were to simplify this, f of -x would equal 0.5 x squared minus 4. Now, does this change this? And the answer is no, nothing changed. So that means this would have to be an even function. And because it's an even function, the graph is symmetric in the y-axis because the y-axis is the line of symmetry, cuts it in half on both the right and the left side. So that is our lesson on linearity, intercepts, and symmetry.